We are now going to talk about something rather subtle: pass by reference, pass by value, and in-place operators. First, it is important to emphasize that it is completely okay and expected that this does not make perfect sense the first 10 times you work through this. For more information, we encourage you to do some searching online. For instance, the answers provided on the Stack Overflow post are a good place to start. It's where I started when I was looking at this. And you want to play around with some of the simple code that we have below to build intuition. There is very little substitute for some time and patience in learning this correctly. Here, we seek to just build some basic intuition about what is going on so that you can be aware of some potential pitfalls. Now, we are going to describe pass by value and pass by reference in a very kind of metaphorical, allegorical way initially. So pass by value is maybe best thought of initially. Suppose that you are the function and I pass you information that is written on paper. Now, if I am passing it by value, what I would be doing is copying something from one piece of paper, let's say my original piece of paper, onto another new piece of paper and handing that copy to you. Maybe that information includes that the variable x is equal to 5. But this information is now on the copy paper which I have given to you. So it is effectively your piece of paper. You can do with it what you please. Whatever you do on your paper doesn't change what's on my paper, because I just gave you a copy. There's two pieces of paper, mine and yours. And let's say that you take your piece of paper and you decide, I want to multiply x by 2. So suppose you just erase that x is equal to 5, and instead you write x is equal to 10 on your piece of paper. If you return that piece of paper to me, this does not change what is written on my piece of paper, because I gave you the value of x. I said x is equal to 5 on your piece of paper. But it doesn't change what's on mine no matter what you do to your paper. It's your piece. You can do with it what you please. I could look at yours and say, you know what? I want to reassign my value of x to be what you decided it should be. That's my choice to make, but you don't get to make it for me. That effectively summarizes what happens when I pass you, the function, a variable by value. Now, pass by reference is when I give you my original paper, which has something written down on it like x equals 5. I've handed over control of what happens to that piece of paper to you. If you decide to erase and replace my x equals 5 with x equals 10 and you give me the paper back, the paper I now have, because I never made a copy, now contains this updated information about x, regardless if I wanted it to or not. You made the decision for me. That's effectively what's happening with pass by reference. So what is the moral here? If I do not want your function, you, if you're the function in this case, to change my information about x without my consent, then I should have passed it to you by value at the beginning, or at least made a copy of it, which is something we'll come back to when we talk about classes in Module 4. Now, at a technical level, if we actually want to speak about this very specifically with Python code, pass by value means Python creates a new copy of the variable within the function. Or, in other words, a new paper is generated, used to track the variable information so that the original variable information is not necessarily changed. Now, when is this the default behavior? When the variables are immutable data types, meaning that the value is left unchanged by the function. What are immutable variable types? Strings, floats, and ints. Those are immutable variable types. Most other variable types are mutable, and their default behavior when passed to a function is to be passed by reference. That means Python passes the memory address, the location. It's like handing over the paper, because it actually just says, instead of me telling you what the value is and you writing it down, or me copying it down to a piece of paper and then giving you that copy, I'm actually handing you the piece of paper. I'm handing you the place in memory where this variable exists. So now the operations that happen may actually alter the actual variable in the location of that memory. So that's my original paper. It's passed to you. That's passed by reference. Now, this can cause some very different behavior than you might expect about what's happening to that variable in your global namespace when you do certain in-place operators, which is something we'll see below in the code. So classes, lists, numpys, arrays, these are passed by reference by default. I should have also added, I believe, tuples, tuples, however you want to say that. Those are also immutable data types compared to lists, numpy arrays, and classes. So the objects that are passed by reference by default, they're immutable data types, and that means they can mutate, change after creation. And this is related to a thing called scope. What is this thing called scope? Python variables created within a function have what is called a local scope. Scope refers to the visibility of variables. We've actually already seen a little bit of this before with myFun1, myFun2, these functions we were creating up above in this notebook and discussed in the previous videos, where we created this value z that was the output that was returned, but that variable only existed within the scope of that function. So basically, scope just refers to, again, the visibility of variables. In other words, which parts of your program can see or use that variable. Local scope usually means only the called function knows about these variables created within it, like that function, that variable z that we were discussing in other videos in the above part of this notebook. They're usually visibly hidden from the rest of the code. So that's it for the first part of this video. Just pause here. You might want to rewatch this, and you might want to read this on your own before continuing to the next part of the video. We are now going to explore mutable versus immutable data types along with in-place operators inside of functions that also allows us to explore scope. All of the things that I was just talking about in the first part of this video. If you did not already run the first code cell in this notebook, which is already at the top that imports numpy as np, I provided another code cell here for you to run that imports numpy as np. And that way you can create an array that is shown below here in one of these code cells that will create a numpy array, which is a mutable data type, as opposed to an integer, which is an immutable data type. That way we can start to explore the differences. Okay. So in this function, which is a scope test, which is just meant to illustrate things involving scope in mutable versus immutable data types, we are passing a parameter called var, short for variable, to this scope test. We are then using an in-place operator, which means times equal. Operators like times equal, divide equal, plus equal, minus equal, those types of operations are called in-place operations. And they are acting on the object in memory if it's a pass by reference type of object, such as a numpy array or a list. If it's an integer, a float, a string, or a tuple, then this doesn't matter. And you can't actually even use this on some of those types of data types. So this right here should actually be changing the variable in the global namespace, kind of outside of the scope of the function, if it's a mutable data type. However, if it's an immutable data type, then this operation should not change the actual variable that was passed to it outside of the function, because we're not returning anything from this function. It's a blank return. In fact, if you don't have a return here, that's equivalent to this function. The return is optional if you're not passing anything back from the function. I think it just helps with readability to know when the function ends deliberately by having a return. But you could just continue on with your code and not have indenting. Just that's gobbledygook that won't run. But again, Python interprets everything through indenting. Again, I just think that having a return just very clearly signifies that the function is over. You're not returning anything. We're just operating on variables to make a point. The other thing we're going to do is then just set the variable a equal to 3. And that's to indicate that we're creating a variable named a. We're assigning it the value 3 within the scope of this function. So this variable a is only understood within this function, whereas the variable var that's passed to it is known as var within the function. The reason I'm doing that is because you'll see in the code I'm creating outside of the function variables named a. Those variables exist outside of the function, outside of the scope of that function. Within the function, if I pass a to that function, as you see I'm consistently doing outside of that function, or I'm passing it other things, that has no bearing on what a is here. The a doesn't even exist inside this function until I create it and assign it to the value of 3, because it's not passed as a parameter. Just something called var is. So var is getting the value of a, either by value or by reference in these other code cells. But then it's just var. A does not exist until line 9 of this function. I cannot emphasize that enough. I am now going to run this code cell. I've created scope test. I'm going to print what the variable is that's passed to it. I'm going to do the in-place operator, which is mathematically equivalent to var equals var times 2. But programmatically, this is an in-place operator, which is something different. We'll get to what happens in a second scope test when we replace this with the mathematical equivalent operator, var equals var times 2, which has different programming implications. So then we are going to say within this function, what have we done to this variable? What have we changed it to be? And then we're also going to say what we've made a to be, and we're going to create a variable a. So I've run this code cell, I believe. Yes, I have. I'm going to create a's that are immutable, like integers. I'm going to create a's that are mutable, like NumPy arrays. And then I'm going to print what the value of a is in the code cell before I call the scope test. And then I'm going to print what a is after the scope test. So let's just go ahead and run this. See what's going on. So before the scope test, a is just the integer 2. That's exactly what's printed here. That's coming from line 3 of this code cell. And now the variable passed to the scope test is var equals 2. That's exactly what I'm printing, here. I'm printing var equals 2. That's coming from the lines 3 and 4 of this scope test function. I then multiply var by 2 and store that as the variable var. I then print that again. So you see, var has been changed to 4 within the scope of the function. Within that scope of the function, I then define a new variable a equals 3. And then I leave the function, right? After I do this, I then return, I don't return anything. And we can see that the variable a after that scope test is still 2, because it was an immutable data type that was passed to the function. However, if a is a NumPy array, so here I'm making it a NumPy array. You can see I'm passing this list 2s and 2s. Like, what is that actually doing? So when I say 2 and 2, that means I want to have a 2 by 2 array of 1s. So here it is. It's a 2 by 2 array of 1s. All 1s inside of the 2 by 2 array. 1, 1, 1, 1. That's before the scope test. Then I have the variable var in the scope test that has now what a is. 1, 1, 1, 1 as the 2 by 2 array. I multiply that by 2 using the in-place operator. That now changes var to 2, 2, 2, 2. Within scope test, I create this variable a that's 3 and I print it. After the scope test, look at a. It's now 2, 2, 2, 2. Before the scope test, it was 1, 1, 1, 1. So what happened here? Well, right here, after the scope test, it got changed, even though we didn't return anything, because of what happened within that function. Because this is a mutable data type, it is passed by default as reference, passed by reference. So when this in-place operator took place in the function, this was actually acting on the location of this in memory, where this variable was being held in memory. It had that piece of paper, metaphorically speaking, and it changed it, whether I wanted it to or not. So even though this function returns nothing, it did have an impact of changing this variable outside of the function. That is what happened. And you could say, what happens if I take a variable a, let's say I take b and I multiply it by 2 to a. And I can print A, like this is not an in-place operator. This is not times equal, this is 2 times A. And I'm going to pass B to A. I am then going to look at what happened after scope test B. I'm going to look at what happened to A, and then I'm going to also print B. And we're going to figure out what's going on with this. Let's just look at this real quick. Before scope test, we have A as our 1, 1, 1, 1, 2 by 2 array. These two lines of code should be pretty obvious. We took B, took it and assigned it 2 times A. So B got assigned 2, 2, 2, 2. That is what got passed to the scope test. So the variable here is 2, 2, 2, 2. We multiply that by 2 throughout within the scope test with the times equal, so just going back up here to this function, times equal 2, which component-wise multiplies, element-wise multiplies to that array. So here is our 4, 4, 4, 4. Within the scope test, we make A equals 3, which of course doesn't impact whatever A is outside of that function. Now look at what happened to A. It's 1, 1, 1, 1. It didn't get changed. We passed B, which is 2 times A, and then we took A, and we said, what happened to A? Nothing. Nothing. But B is now 4, 4, 4, 4, right? B was 2, 2, 2, 2. It's now 4, 4, 4, 4. What happens if you make this to, if we make that A 2, that's the way to do it, really. And then, actually here, I'm going to do it like this. That's B, and we're going to make B equal to A. All right, so we assign B to be what A is. We then do times equal to, so again, this is an in-place operator. And now let's see what happens. A and B are now both 4, 4, 4, 4. So when you create a NumPy array and you assign another variable equal to that NumPy array, you might be thinking you're making 2 copies of this 2 by 2 array of 1, 1, 1, 1, which is what that should be. But what you're actually doing is you're just assigning other variables equal to the location of this original mutable data type in memory. That's what's happening. So now whenever I change B with an in-place operator, it's also changing A. I could keep going. I could make C equal to B, D equal to C, and so on. And then if I change whatever the last one is, it's changing all of them. That's kind of a bit of a problem. I mean, maybe it isn't, depends on the purpose of how you're designing your code, but it's something to certainly be aware of because you may not be intending for all of that to happen. So again, I'm going to keep going. There's other parts to this video, but this part you definitely might need to watch a few times and read through this and do your own experiments to really drive home the difference between what's going on with local scope, which probably isn't the more confusing part, but more the pass by value, pass by reference, and what's going on with the in-place operators. The next part of the video can offer some additional clarity to what's going on in terms of how you can remove this behavior if it's undesired by avoiding the use of in-place operators. So you might be asking right now, wait a minute, what if I want to do local work to a mutable data type inside of a function? So for instance, I want to operate on a NumPy array, but I don't want to have that change reflected back after the function exit, after I've returned from that function. The answer is simple. Do not use an in-place operator like plus equals, divide equals, times equal, etc. Don't do it. Instead, use something like var equals var times 2 in the context of the scope test example we have, because that creates a local copy of the mutable data type, and it will then, in this case, in this very specific example, multiply 2 to every entry. So here's a simplified version of a second scope test compared to our first scope test. We're going to take a var in as a parameter, and we're going to then multiply it by 2. And if this is mutable, it will simply create a local copy. And then, right, it's returning nothing. This shouldn't change the variable outside the scope of this function. This variable is equal to 2 times whatever was passed to it, but we're not using an in-place operator, so it's not going to actually act on that object in memory because it creates a local copy. This is like creating another piece of paper where the action takes place, where things are written down, but it doesn't change what's written down on kind of that original copy of paper, using the original metaphor that we were talking about. So if I run that piece of code, and now I'm just going to create a 3x3 array. That's basically an identity matrix, a 3x3 identity matrix. I'll just go ahead and run this so you can see. So you can see it's 1, 1, 1 on the diagonals and 0 everywhere else in this 2D array. I'm just showing you other things that you haven't seen yet with NumPy arrays. I'm always trying to show you something new, even when I'm using kind of things like libraries and packages we've seen before. So that's 1, 1, 1 on the diagonal, 0 everywhere else. If you multiply that by 2, you expect to see 2's on the diagonal and 0's everywhere else. And then after the scope, even though this is a mutable data type, I'm not using the in-place operator of times equal, I should still see that A is this original A, 1, 1, 1 on the diagonal, 0 everywhere else. And that's exactly what you see. After the scope, nothing changed. So inside the scope test, clearly it multiplied it by 2. And if you need to see that, here, I'll just print var. And if you run that, you see there's my A. Here's my printing from inside the function. You see it's all 2's, but it didn't actually change that A outside of the function, outside the scope of that function, because I'm not using an in-place operator. That's pretty much it. That's what you want to do. So like here's a strange list, right? So here I'm taking a list, and I'm going to run a scope test. So this is hi, 3, and I'm actually even passing a function, right? A list can have all sorts of things inside of it, even a function, a user-defined function. And if I pass it to the original scope test, what do we know about multiplying a list by an integer? Well, it's just going to create like 2 times that list. That list is basically copied twice inside a larger list. And if you look at this inside the original scope test, oh, I've disconnected from my runtime before. Let me go run my function. I'm sorry. I'll just go run this real quick. So bear with me for a second. Here we go. Run that there. We'll just go ahead and I'll use this to jump down. Here we go. There we go. Run down. Here we go. So now I'll run that, and you can see I have a function, which is certainly there's just a memory address there. And then you see I just have that same function inputted twice along with the high end of 3. Like that. That's what happened with that variable when I multiplied it by 2 inside that original scope test. And after the scope test, that list has been changed because that list is a mutable data type. Within the scope test, there's that other variable A that's created, but it only exists within the scope of that test, with that function, excuse me. But again, if I take that really strange list, I just make it high as a string, 3 as an int, and my fun1 as a function, and I pass it to scope test 2. Then when I run that, I see I have not changed that very strange list, that mutable data type, outside of the scope of that function, because I didn't use an in-place operator. So that's it. If you don't want this behavior like this to take place from our original scope test, don't use in-place operators. That's pretty much it. Just avoid it, and then you won't have to worry about this behavior. We end the final third video for the Part A lecture notebook on this instructor-led activity, to use or not to use in-place operators in functions. I'm just going to go ahead and give myself more space here. The simplest formula for the height of a falling object under the influence of gravity and dropped from an initial height is given by h of t equals h of 0 minus 1/2 times g times t squared. Excuse me. H of t is the final height of the object at time t. H of 0 is the initial height of the object when it is dropped at time 0. G is a gravitational constant on Earth. This is approximately 32 feet per second squared, or 9.8 meters per second squared. It depends on what units you're using. T is the total amount of time the object has been falling in units of seconds. This is a rather crude model as it assumes the object falls in a vacuum, meaning air resistance is neglected, and h of t can be negative if we choose t large enough, which is kind of silly. However, Despite these crude aspects of the model, we will use this formula to estimate the final heights for some objects falling over various amounts of time while subject to different gravitational constants and drop from different heights. However, we have two separate objectives. One is to predict the estimated distance that traveled for objects that are not yet falling, while the other objective is to update the distance traveled for objects that are already falling. Below, we want to create two functions, predict underscore distance and update underscore distance, that perform element-wise operations on NumPy arrays of h, g, and t values. And I should really say that the h is referring to h of 0, and t is saying where you want h of t to be, the final time. So you want to use an in-place operator to update the array of h values directly in the update distance function. So you're saying, I have some objects that are falling. Here is where their initial heights are at the moment when I'm tracking them. And I'd like to say what they are after t. You want to update those directly. That's what you want to do in update. Whereas in predict, you don't want to change what those h of 0 values are because you haven't actually dropped anything yet. There's nothing to update. You just want to predict. So there you should not use an in-place operator. So at this point, I'm going to pause the video. You should really try this for yourself. And when we come back, I'll show you the solution. I hope you tried this on your own. Here are the solutions that I have. If we want to predict the distance, then we want to use this function where we pass h, g, and t to the predict distance function. We compute the new height, which is given by the initial height array minus 0.5 times g times t squared. Remember, we use times, that two asterisks in a row, to raise t to a power. And then I'm going to return h. Now here, when I want to update the distance, I use an in-place operator. This is mathematically equivalent to h equals h minus 0.5 times g times t squared. However, with that in-place operator, when h is an array, this will create an in-place change to what the value of h is. It's changing what h is in memory if h is mutable, such as a NumPy array. So if I create both of these functions right here, and I just ran them to create them, and then I created an array of heights. So let's say I create just, I'll do it as NumPy arrays. It's easier to work on these things if they're NumPy arrays. You don't want to use lists. Let's say I make a height of 10 and 20. Let's say I make g is just, let's say 1 is in different units actually. So let's say that we have the 32 and the 9.8 because we're maybe using different units for these different heights, like one's in meters and one's in feet. So I'm going to just code up these different values. And then let's say my time for these different experiments is going to be, let's say 1 second and let's say 0.5 seconds. So I'm just representing different results for different experiments based on different units of measure in terms of meters or feet. So let's say I have those three arrays, and now let's look at printing what the output is of predict distance for h, g, and t, and I'm also going to print what h is. And when I run this, you will see that I'm outputting a new set of two values, -6 and 18.775, but I've left h as 10 and 20. I didn't use any in-place operator here. So even though h has been updated within the scope of the function, because I didn't use an in-place operator, it didn't impact anything outside the scope of that function. However, if I run update distance, so I'm just going to go ahead and copy and paste the contents of this cell into here. I'm going to change this to update distance. And, oh, this is perfect actually. I'm going to leave this in here as this part of the video. I got a ufunc type error. This might seem very strange, and I actually point out in the next activity that you will also likely encounter this type of func error. This is a ufunc multiply error, and here I'm actually getting it as a subtract error. Same difference. It's something you're expected to find. When you're using an in-place operator, this is a little interesting here. I have floats here. Notice these are going to be NumPy arrays with floats, but I'm updating an array that certainly has a data type of int. This certainly has a data type of int, right? Because these are two integers. So this is the D type for that is an integer, whereas the D type for these is float. And if you remember the D-type data attribute, this is going back to module 2. And if you work with an in-place operator, which means it's trying to update the thing in memory, this was stored with a certain amount of bytes in memory based on these being integer types as opposed to floating point types, which take up more space in memory. And that's a bit of an issue because the data type clearly has to change to floats, as you can see that's coming from here. So the way around this, the way you have to deal with such a ufunc type error is if you see that you have arrays and they have different data types, and you're going to do some sort of like in-place operator, and you are going to deal with this, is you should store this as type float. In fact, I don't think I need to write. Let's see what happens if I can't remember if I do it with float as if it's that or if I just say float. I think I just do it as type float. Yeah, there we go. I think if I do this as if it was a string, I think it still works. We'll see. Yeah, you can see, notice that's 10 point and 20 point. That's interesting how flexible that is, but I kind of just like it like that, like float, same thing. Just run that, it's 10 and 20. So notice I haven't changed it here, it's 10 and 20. I should get rid of this ufunc type error. If you can look up what this is, you can search Stack Overflow, but it's really, you're basically saying you're trying to convert. This is basically what it's trying to do. It's trying to cast the output from a float to an integer, because this is an integer and it's trying to cast this into this because of the way the memory operation's working. But the casting rule is like, it's got to be the same kind. This is making it the same kind, this as type float. So I'm glad I came up with that error. I wasn't expecting it when I created it. I just kind of forgot about it, but I remembered it was also something that was in here, and I even had a note about it inside of this function, that you cannot do it. In that case, it's coming from a multiply if you do this one correctly for investment functions. All right, let's run this now. You'll see that error should go away. There you go. So that was the output, same output as before, but now when I print age, notice it's been changed, right? Because I updated the distance. I did it with an in-place operator. And in fact, here, where I'm returning an h with the predict distance, I can actually change this. I can make this, I don't have to return h at all, because h is getting changed, because we're using an in-place operator. So if I run that and I don't even return h, let's just go through this again, because I've changed h. This will make h back to 10 and 20 as floats. When I run that, I go through here, and then I run this again, notice nothing is returned. If you don't have any type of return, if you just return nothing, or you even get rid of the return, then a none type is returned. None. Nothing is returned from this function. So when you print the output of a function with no return or a blank return, none is what you get. There's a none type. There's a certain type of none type, which is a very useful default type of variable for certain functions. Anyway, or a certain type of parameters for functions. But notice the h is still changed, right? I didn't have to return h at all. So that's something to kind of work with and play with. Hopefully that made sense. I know you might have to watch that a few times, and it's going to take some time for some of these ideas to sink in. These are some subtle concepts that we touched on in this lecture notebook. So good luck with activity 4. There is a solution video for that. It's in the playlist. I'll link to it on Canvas as well. But give it a try on your own. It's very similar. Instead of dropping things from a height, I'm doing things involving compound interest, and I'm asking you to either predict a balance, basically do a projected balance, or update a balance. So conceptually, it's very similar, only mathematically the formula has changed. And what you might do, what you want to do is you just want this final amount to be basically the new principal or projected principal for like what the final amount is. So you might think of that A as like P at a final time. That might be P of T, and this is P of 0, in order to connect that conceptually to what was going on here with H of T and H of 0 right there. So that's it. Good luck. Thanks for watching.